There we go. Okay, so as we get into kind of what this entropy means and how you can get like even just a rough idea of how much entropy there is. So when you look at like, we're going to look at like different reactions. And so even if you don't know the numeric values, a lot of times if you just look at the state that everything is in, you're going to get an idea of what's taking place, okay? So like, and here's your general mode. If you have a solid, okay, like a golf ball, right? The particles that make up this golf ball have a certain amount of entropy. They have a certain amount of disorder they can move around it. Obviously not very much. It isn't like all of a sudden, you know, I'm going to look at that golf ball and it's going to start like moving on its own, right? If that did, there are other things going on. Liquids have more entropy, but you're somewhat limited. Now, if you look at the substances that you deal with in your daily life, most of them are either solids or gases. You actually don't deal with that many things that are liquid at room temperature. Yeah, you have water, you have blood, bodily fluids, whatever, okay? You know, things that you drink, but those are all pretty much water-based. So the vast majority, if you think about it, of the interactions that you have with physical substances are pretty much either solids or gases. Yeah, we have this atmosphere, that's kind of a cool thing, right? So you breathe in, you breathe out, okay, hey, you have an exchange of gases. But here's what's most important is that when you compare gases, because of the fact that they are free to move around, have a tremendously high amount of entropy, okay? So these are like little Timmies on steroids, okay? They're just going to be bouncing around all over the place. Okay, so even if you're just trying to get an idea of, okay, which one has a higher state of disorder? So if you were to compare 1 mole of hydrogen gas, okay, so you've got 1 mole, like enough to fill up kind of that water jug on top of the cooler, okay? If you were to compare 1 mole of hydrogen gas either under a pressure of 1 atmosphere or a pressure of 5 atmospheres, which do you think would have more positional entropy? The 1 atmosphere or the 5 atmosphere?
5.
Why?
Has
More stuff moving around.
But
It
it's
has-
still 1 mole though.
It has more
I mean,
microstates to fall around.
One is the same as one.
It's still the same number of particles.
It's less
Oh, then one.
or just less volume.
Yeah. So your 1 atmosphere is going to have more positional entropy than the 5 is, because of the fact that if you were to try and make that under 5 atmospheres, you'd have to decrease that volume. So 1 mole is going to have more than the 5, or 1 atmosphere is going to have more than the 5. Now, what's this going to have more entropy? 1 mole of gas at 5 degrees Kelvin or at 100 degrees Kelvin?
100.
100, right? There's more energy. There's more places for them to move around it, okay? They're just going to have more random motion. So as temperature increases, your entropy increases. Now, here's a simple one. Solid carbon dioxide, otherwise known as dry ice, okay? Dry ice, okay? All carbon dioxide is dry ice. There's solid carbon dioxide. And then it goes directly into a gaseous phase. So clearly, your gaseous CO2 is going to have much more entropy than that solid CO2. So solid CO2 will still have some, it just won't have very much. Okay, got the idea.
Got it.
Got it. So, now, here's what's going to be important on this one. So now I want to try and just be able to predict what's the sign of delta S. What's going to happen now? Notice this is not the entropy, okay? This is the change in entropy, okay? And that's going to be important, okay? We're not necessarily talking about the entropy itself, but we're talking about the change in the entropy, okay? So, salt's going to dissolve in water. When that salt dissolves in the water, in terms of the salt, is that going to be more, are you going to have more entropy or less entropy from the salt's perspective once that dissolves?
More, because you're turning it, you're combining it with the liquid.
Well, yeah, I mean, if you look at what happens, okay, what physically happens is that you have this structure of chloride ions and sodium ions, right? Okay, if you've ever looked at salt underneath a microscope, it's these nice little cubes, right? And so you have this lattice of sodium chloride, right? They're all bound together, okay, locked up in place. Okay, cool. Now, so that doesn't have very much entropy, a little bit, but not much. So then you put it in water. Okay, well along comes a water molecule, right? Hydrogen, oxygen. So you have this dome of negativity. It's going to attract to the sodium. So here's what has to happen for this to dissolve. Okay, it's a tug of war. Basically, that sodium has to have a stronger attraction for the negative into that water molecule than it does for the chloride ion. Because if that had a stronger attraction for the chloride ion, then salt would not dissolve in water. Okay? It's like, well, what's the point in adding salt to your food if it doesn't dissolve, right? So the whole point of salt working is because of the fact that it does dissolve. Okay? So now that sodium and chlorine are now like, they're latched onto these water molecules. So the water molecules are going, okay, right, we'll take you on, okay? So the sodium ion's going, great, I'm with Wally, the water molecule, we can move around, we're a liquid. It's like, you know, see you later, chlorine, I know we've been together a long time, but I'm out of here, okay? We're going to go hang out with water molecules. So from the salt's perspective, from the sodium chloride perspective, that entropy increases, okay? But from the water molecule's perspective, the entropy actually goes down some. Because now they've got to drag around these sodium ions and these chloride ions. So from the water's perspective, it actually decreases the entropy because they're not free to move around. So it would be like you're getting ready to go out on prom, okay, right? You're all excited. You've done hair, tuxedo, the whole smash, right? You are all ready to increase your entropy. And then just as you're ready to walk out the door, mom and dad go, hey, you need to take along your little brother. Something's coming up. You need to take your little brother to prom. And your little brother's all hyped, right? Because this is like the sodium ion. Because they're all hyped up. Like, oh, little brother's going, I get to go to the senior prom, right? Because his entropy is going to go way up because otherwise he was going to stay at home that night. So from your little brother's perspective, entropy goes up. But from your perspective, guess what? Your entropy goes down. Because now you're going, well, doggies. I gotta take along little Timmy. So whether that entropy goes up or not kind of depends upon your perspective. So purely from the salt perspective, you're going to get an increase in entropy. So is that going to be a positive delta S or a negative delta S from the salt's perspective?
Positive.
Positive. Okay, so that's going to be a positive delta S. So we're going to take iodine and we're condense it into a liquid from a gaseous phase.
It's going to lose it.
So entropy is going to go down. So delta S is going to be a
Negative.
negative delta S. Okay. We're going to make a precipitate of silver chloride.
It's going to go down.
Yeah, because you're going to go from having random silver and chloride ions into, yeah, so that can be negative delta S. So that's one of the things that you've got to be able to do is be able to look at a situation and go, okay, what's actually taking place? Is my entropy increasing or my entropy decreasing just based upon the physical situation? All right. Now, so we can actually learn a lot about what's going to happen if you look at melting ice. Okay? So if you look at what physically happens to a piece of ice, I said, all right, class, here's what we're going to do for a lab. We're going to melt ice.
We did that in Chem April.
Yeah, where you put it on the little, yeah, okay. So we're looking at a little bit more advanced than what happened to Chem 1. Okay, so here's the deal. So, and there's a whole bunch of things that play into something that seems pretty simple. It's like, okay, hey, ice is going to melt. But it's actually a fairly complex process. So let's start with this idea. We have to figure out the direction of the energy flow, okay? So the direction of the energy flow, is that going to be from the ice into the air or from the air into the ice?
Air into ice.
Or liquid or whatever that is, right? Okay? So here's what's going to be important. So the energy around the outside is going to flow into the ice. Okay? If you're trying to make iced tea, your tea would lose that energy and it would flow into the ice. Okay? And this is what we talked about. Temperature, you can view temperature as an indicator of direction of energy flow. Okay? So the energy is going to be flowing into the ice. Okay? Nice. Now, here's the deal. So we're going to look at the system. So, Mr. Avery, when that ice melts, what's going to happen to the entropy of the ice?
It's going to increase
Why? You're right, it is. But why are you right?
because it's going from a solid to a liquid.
Okay. So from the ice perspective, we're going to increase entropy, right? So from the ice perspective, we're going to increase entropy. We're going to have a positive delta S because we're going to go from those water molecules being locked into a lattice structure, held together with a bunch of hydrogen bonds, into a liquid. So it's still going to be a liquid, right? Okay. So they're not completely free, but they certainly have more freedom than if they're locked up. Okay, because they're going to be attached. So it's like, it's like you got to take your little brother to prom, and you can't just turn him loose. So you're going to have like one of those wrist things, like on a piece of string to keep track of where Timmy is. So it's like you can move around, Timmy, but we still have to stay attached. Okay. I think more children should be put on those anyway. All right. So this is why I'm single. Okay. All right. So now. But let's look at what happens to the surroundings. Okay? What's going to happen to the entropy of the surroundings?
It's going to go down
It's going to decrease. Why?
because it's transferring its energy, so it's at a lower energy state.
Beautiful. So the surroundings, okay, because they're losing that energy, you're going to decrease the entropy of the surroundings because that energy has been lost. So from the surroundings perspective, you have a decrease in entropy. Okay? Now the same thing happens if you look at when you work out, right, you sweat. What's the body's function of sweating? Cool you down, right? So that sweat is designed to evaporate. So so it's a similar type of deal. So when you sweat, you form perspiration. It dries. When it dries, that's evaporating, which means you're going from a liquid into a gas. That's increasing the entropy of the system, right? Where does it get the energy to break the bonds?
From the surroundings.
From your skin, right? So your skin is giving up that energy. Your body is giving up that energy to allow that water to evaporate.
And that's why you get tired, because you're giving up energy.
Well, kind of, yeah.
If you think about it that
Yeah,
way.
there is at some degree, yes. That's true.
That's a lot of library.
So you're decreasing the entropy of your skin because of the fact that it's losing that energy to break the bonds to allow the water to evaporate. Okay? So here's what I want you to see, is that if you increase the entropy of something, you have to decrease the entropy of something else. Okay? It's just like if something gains energy, something has to lose energy. If something increases entropy, something has to decrease entropy. Okay? Right? Okay. Now, so for your delta S from the system, that's going to be a positive now. From the surroundings, that's going to be a negative. So if you're going to try and figure out the delta S for the surroundings, you need to look at what's going to happen with temperature. Like, for example, you take a bowl of hot soup and you set it out on the countertop. What's the soup going to do?
Hold on.
So what's going to happen to its entropy? It's going to decrease. Where is that energy going to go? So the entropy of the surroundings is going to go up. So the other way to look at temperature is that it gives you an indication of what's going to happen with the entropy changes. Okay? That's another way to look at it. So if you have hot soup, put it outside, it's going to cool down. You have a bowl, excuse me, you have a bowl of ice cream, what's going to happen?
It's gonna melt.
It's going to increase.
It's going to increase in entropy, but the surroundings is going to decrease. Okay, got the idea. Now, let's talk about an exothermic reaction. So this is where some random things all kind of come back into focus here. So, Tate, you've experienced a very exothermic reaction, right?
I have.
Okay, up close and personal. So you have an exothermic reaction for the explosion of hydrogen and oxygen, right? Okay, so from an entropy standpoint, that air around it got really, really heated up really, really quickly, right? And it was an explosion. So you went, okay, the balloon went flying apart, okay? Tate's hair probably even got messed up, right? We greatly increased the temperature of that area right around that hydrogen balloon, okay? That was some serious increase in entropy. Okay, so the delta S for the surroundings is a positive value. So if we're going to increase the entropy of the surroundings, guess what? We have to decrease the entropy of the system. So if you look at what happened, okay, and this is a simple example. So if you look at the balanced equation, it's 2H2 plus O2 yields 2H2O water, and that's going to be liquid. So these are gases, okay? So here's what happened. From an entropy standpoint, you have 3 moles of gas on the reactant side. You have 2 moles of hydrogen, 1 mole of oxygen. So you have a whole bunch of gaseous particles with a very, very high degree of entropy. Out of that, we're going to make liquid water, okay? So we're going to go from 3 moles of gaseous reactants into 2 moles of liquid. So what do you think is going to happen to the entropy of the system?
It's gonna decrease.
It's going to decrease greatly, okay? Because you went from having 3 moles of gas to 0 moles of gas, which is a pretty big change, okay? So guess what? The system's going to lose that entropy. Where's that entropy going to go? Oh, it's going to go to the surroundings, because the surroundings are going to be in chaos now. We're going to have bits of balloon flying around, okay? You're going to feel this heat. The air molecules are going to be going, oh my God, I've gained energy, okay? Right? And they're going to start bouncing around like crazy banshees. And so, but the hydrogen and oxygen are going, I'm kind of chilled out at this point, you know? I'm locked up into a water molecule. Good, okay? So that's always going to be your trade-off. So not only do you look at exchanges of energy, thermal energy, you can also look at exchanges of entropy. Okay, so the other side is true. Is if you have an endothermic reaction, okay, so if you look at that reaction that you all did with like the copper sulfate in the water, you dissolve the copper sulfate and finish it down. So if it's an endothermic reaction, which direction does energy flow? Into the system, right? So the system's gaining entropy, right? Okay? But the surroundings are losing it. So endothermic and exothermic not only indicate the direction of energy flow, it also tells you what's going to happen with the entropy. Okay. So, if there's one equation that you need to write down, and this will make sense in just a second. So delta S from the surroundings equals negative delta H divided by temperature. Now let's look at what happens with the units, okay? So if you look at this in terms of this negative sign, right? And there's a negative in front of this. So your units are going to be kilojoules per mole, but then we're going to divide by the temperature. And what units do you think the temperature has to be in? Kelvin, okay? So typically these are pretty small numbers. So typically that's written as joules per mole Kelvin. So delta S is typically going to, this is how you're going to see it measured in joules per mole Kelvin. So that's what I pointed out on your data table in the back of that book, Appendix C. So your delta G values and your delta H values are going to be in kilojoules per mole. Only your entropy is temperature dependent, but that's also in joules per mole Kelvin because it tends to be a smaller number. Now, here's the deal. If you look at the Vernier catalog, you can measure, you can buy temperature probes, you can buy pH probes, you can buy pressure gauges, you can buy calorimeters, okay, all of this stuff. What you cannot buy are entropy probes, okay? They don't exist, okay? They're not there.
Why not?
Just because we can. How about that? Okay? So, but here's what we can measure, okay? We can, and you all have done this, and this is kind of why I did this in the sequence that I did. You all can calculate delta H, right? You can calculate delta H. We can get that number. Then if we know the temperature, then it's just dividing that by that temperature. Voila, oh, there's my change in entropy. So we can't measure entropy directly, but we can measure the impact on the delta H. Now, here's the importance of that negative sign that lurks out there, okay? So this is for the surroundings. So this is why it becomes like a negative of a negative, right? So if you have an endothermic, let me get rid of this. If you have an endothermic reaction, okay, delta H is, for the system, is going to be a positive value, okay? It's an endothermic reaction. Energy is going to be flowing in. But we put that negative sign out of that, so that way the delta S for the surroundings is going to be a negative value. So if it's an endothermic reaction, this is why you got to understand the significance of this negative value. So delta S from the surroundings, and that's the only thing that we can measure. So we can calculate delta H if it's an endothermic reaction. Delta H is a positive value. We divide that by the temperature, whatever that temperature is going to be. Okay, it's going to be standard temperature, which is 298 Kelvin, which is 25 degrees Celsius. So that's why that negative sign has to lurk out there, because then you're going to switch the sign. So if you have a positive delta H, and this is, you've got to think this through. Right, I got a positive delta H for the system, okay? Which means it's going to absorb energy, so it's going to increase its entropy. But the area around it is losing that energy, so it's going to have a negative delta S for the surroundings. Now the opposite is true. The hydrogen and oxygen blew up, right? Big boom. Hydrogen and oxygen went boom, right? When that happened, guess what? The surroundings had an increase in entropy. So it's an exothermic reaction. We have a negative delta H. So we take a negative of a negative. Delta S for the surroundings goes positive. Okay? So that negative sign there isn't just a typo, or it isn't just some random negative, oh, we'll just throw a negative sign in there, oh, what the heck, you know, what's a negative sign between friends? No, there is a reason for that. Now, what if delta H equals 0? there's no change in entropy because heat isn't flowing in or out of the situation. Okay, so this is a situation where I can't measure the delta S for the surroundings directly, but I can look at what happens to tape. Basically, I set off the hydrogen balloon. Oh, tape got warm. His hair got messed up. There are bits of balloon flying everywhere. So the entropy then for the system decreased. The entropy for the surroundings became larger because now we're going to increase that entropy around it. So you make observations about what's happening, and then from there you infer what's happening to the system. Okay, so first law of thermodynamics. Basically all it says is that energy is conserved. So, and Einstein weighed in on this equation by saying E equals mc squared. So, what's C in this equation? Speed of light. M is your change in mass, okay? So, you can actually like calculate if I took, for example, the mass of a golf ball and say, okay, hey, I could convert that into pure energy. I could calculate how much energy would be released in conversion of the golf ball into energy. And it's a tremendous amount of, it's a pretty big value. Because the speed of light, remember, is 3 times 10 to the 8th. Or you square that, right away you're at 10 to the 16th power. Okay? You're already pretty big right there. So yeah, so it doesn't take very much mass at all to get you a tremendous amount of energy. So this is what's driving our sun, okay? Our sun's been around for about 5 billion years, give or take about 10 minutes, okay? We should have about another 5 billion years to go. And what's happening in the sun, every second we're exchanging literally tons of hydrogen, is being fused together to produce helium. And there's this tiny, tiny, tiny bit of difference between the energy, between the mass of a helium atom and the 4 hydrogen atoms that make it up. It's called the binding energy. For those of you that are in AP Physics, you'll do this calculation in a couple weeks. Okay?
Have fun.
So here's all you need to know, is that in the fusion process, there's a slight difference between the hydrogen and the helium. You take that difference in mass, put it into this equation, that's how much energy that you get, okay? So, because this is c squared, it doesn't take much mass at all to create a tremendous amount of energy. So, even if you go back into the philosophical ideas of the Big Bang, okay? We think there was a singularity 14.6 billion years ago, give or take a week, okay? Roughly. And then there's a singularity, and the only thing that existed was energy. Okay, it was pure energy. The energy began to cool down, and out of this equation, if you can take energy and convert that back into mass. Now, this is what gets weird that people generally don't have a problem. Most people don't have a conceptual problem with the idea that, oh, I can take mass and I can convert that into energy. Oh, okay, that kind of makes sense. Burning a candle, which isn't what's happening, but they get the point, okay? But when it gets weird is you say you can take pure energy and have mass appear out of it. So this is what happens in the Large Hadron Colliders. So if you have enough pure energy, you can begin to make matter appear out of that. Like you could create an electron out of pure energy, or a proton. Proton has a lot more mass, by the way, so it takes a lot more energy to make a proton than it does make an electron. But this was the great equivalence. So, and this is, you know, philosophically, we can't even begin to wrap our eyes around the idea that all of the energy that existed ever in the universe was contained in one singularity. So out of that, you get all of us, okay? You get the earth, you get the sun, you get countless numbers of galaxies just like ours, filled with planets, filled with stars, okay? So out of that singularity of energy, the universe came into being. And that's tough to get. It's like, wow, even if you just look at our rock that we're on, okay, and it's a cool rock. I mean, it really is. I mean, it's got an atmosphere, we got a moon, we got Jupiter and Saturn out there kind of acting to sweep out a bunch of meteors that might impact us. We have oxygen, which is kind of cool, because if we just had a pure nitrogen environment, we wouldn't be here having this discussion, okay? But we don't want too much oxygen, because if you have too much oxygen, if you ever start a fire, you can't shut it down, okay? So there are a whole bunch of things that put us right into this sweet little Goldilocks zone. And I was actually last night watching a deal, and when bacteria began to produce oxygen in our atmosphere, it actually caused a mass extinction of yeah. Uh-huh. Yes. Okay, I will tell. I might. Kelsey, go down to the library and get your Chromebook. My class got interrupted, so you can go get your Chromebook. Actually, why don't you go and stop that camera for a second? Everybody needs to stand up and take a stretch.
You were saying something about bacteria.
Okay. So, before I was so rudely interrupted again by Kelsey Thurman, more gray hairs with his name. Even when you're not in my class, you cause me to have gray hairs, man. Okay. So, it was basically this huge mass extinction event. Because once you introduce oxygen into the environment, because oxygen acts as basically this huge, reactive process, because oxygen really wants to take in electrons. It really wants to get reduced, okay? That's why we call it like an oxidizing agent. So, but the bacteria and organisms and this is, millions of years ago. But once you develop those organisms that could actually use the oxygen, then they actually thrived, because now you have this huge thing, this oxygen, that was available to use as an energy source. Because that's how we work. So if worst case scenario is we lose the oxygen that is in our environment. We can't do anything with nitrogen, okay? We don't have the capacity to use nitrogen as an energy source in our metabolic processes. We have to have oxygen. And without that oxygen, bad things are going to happen. So once our atmosphere developed oxygen, that was one of the biggest game-changing events that happened in the evolution of the Earth. And you can actually go back and you can find, hey, when did oxygen start to show up? That completely altered the chemistry and all of the organisms that were alive and existing on the Earth at that point. Okay. All right. So, second law of thermodynamics. And this is in a spontaneous reaction. Okay, notice I have the word always in big bold letters here. There is always an increase in the entropy of the universe. And when I talk about the entropy of the universe, I mean the entropy of the universe. Okay? Like writ large. Okay? So like, for example, when I knock my can of soda over, okay? Oh, right? There's been any number of bad things I wanted to say. But that became spontaneous because of the fact that by doing that, I increased the entropy of the universe, okay? The water spilled out. Now, I had to clean it up, okay, which is a non-spontaneous reaction, because as the old saying goes, hey, that thing isn't going to clean itself up, okay? And that's true. It wasn't. If I didn't clean that up, it was just going to sit there.
It would have evaporated in there.
But it still would have left the sugar nasty residue. It still would have been there when you guys got out of here on the last day. You said, oh yeah, Burke, yeah. Yeah, okay. So, when you look at this mathematically, okay, and like I said, if you ever need this equation, I will give this to you, because it isn't on your equation sheet. So, when you look at the change in entropy of the universe, okay, you have two things that you add together. The change in the entropy of the system and the change in entropy of the surroundings. So if you want a spontaneous reaction, okay, if you want a spontaneous reaction, the increase in the entropy of the system, let's say for example, if that's your positive value, that means the surroundings have to have a decrease in theirs, but the increase of the system has to be bigger than the decrease in the entropy of the surroundings. Or the decrease in entropy of the system has to be countered by a larger increase in the surroundings. Here's the driving thing. You can't have both of these being positive. Okay? You can't have both of them being negative. Just like you can't have a re-re action. Okay? You can't have an ox-ox action. Okay? You can have a redox reaction where electrons are gained and then lost. Same thing has to happen here. So if you can calculate these values, and again, that's the toughest part. Okay? And you can understand the concept of entropy, but directly to measure entropy is tough to do. And that's why you had that formula that said, oh, okay, right, delta H over temperature. So we can measure the enthalpy change, because you all have done that, right? You all have done those calculations. Okay, 2 different labs, you all did those calculations. That's something we can do. We divide that by the temperature, then we can get our entropy aspect of this. So there's 3 options that can happen. Delta S of the universe is positive, okay? It's a spontaneous reaction, right? Now, and again, I want you to get out of your mind. Spontaneous reactions don't mean that you don't have to put energy in to start it, okay? It doesn't mean, it's going to happen right away as soon as you mix the things together. You still have an activation energy, like for example, the balloon with the hydrogen and oxygen in it, okay? The hydrogen and oxygen by itself are not going to violently explode, which would be bad, okay? Because let's say that did happen. Well, I've got a big tank of compressed hydrogen gas in the back room. If hydrogen and oxygen spontaneously on contact exploded, okay, guess what? Well, yeah, it's like, talk about a little bit of pressure when I go back there, because what I do is I take like a balloon and I put it over the nozzle, right? Okay? And it was like, but if there was a chance, that as soon as that hydrogen escaped and interacted with the oxygen, it began to explode, well, bad things would happen. Because you pull that off and a little bit leaked out, like, okay, but after working out, I don't know, it's filled a hydrogen balloon. And some of it escaped and spontaneity happened, and now his entropy is spread out.
All over the room.
All over the room. Okay? Which would be bad. Okay. Now, if delta S is negative, okay, in the forward reaction it's not going to happen, but if we can reverse it, then it would be spontaneous, okay? All right? So just like hydrogen and oxygen combine to produce water, and it's very exothermic, and we get a tremendous release of energy, but the opposite is true though too. If I have water and I want to separate it into hydrogen and oxygen, guess what? Then I take that water and I have to put energy into it to push it back up the hill to separate it into hydrogen and oxygen. So do you think, just based upon your casual observations on the 17 or 18 years you've been on this earth, do you think that water spontaneously separates into hydrogen and oxygen? No. No. If it did, would we have oceans?
Yes.
No. Okay? Like, or you fill up your bathtub, right? Oh, I'll take a bath, you come back 10 minutes later, well, where's all the water? I don't know, but there's a lot of hydrogen and oxygen in the room, okay? Yeah, don't light a match, okay? Well, actually you could, because then it would be spontaneous in that direction, and you'd have to like force it to get back into water. Okay.
And then it'd go back into your bath.
And there you go.
And then it'd just be a...
It'd just be a vicious cycle, okay? Now, the other option is that if delta S for the universe could also equal 0, okay? That's a viable option. And if that happens, the system's in equilibrium. Now, what's going to happen here is that's going to happen when you get into phase changes, okay? Like, for example, when you transition from ice into liquid water, or you transition from liquid into a steam, otherwise known as boiling. So you can have that situation, but you're just going to be in equilibrium. Okay. So here's the main idea, okay? Is that, oh, I know where I'm at. Where's that? Not moving. I'm moving it, but it's not moving it on that. That's weird. Okay, that's weird. Why is that? I was on such a roll.
Oh, you got it.
Did I? Hey, we're back. I have no idea what happened. Okay.
It was spontaneous reaction.
It was. Actually, no, it wasn't. Well, pudding was. Okay. So, here's the heart and soul of this, in terms of this room. So, no process that produces a lower state of disorder, entropy, in a system can proceed without producing an equal or greater amount of disorder in its surroundings. So, here's a classic example, okay? So, I come in on Sunday, right? And I clean the room. So you will walk in on Monday, and this room is like spotless. Everything has been put away. There's no loose papers, nothing. So what can you all conclude happened?
You cleaned it.
I cleaned it, right? So I decreased the entropy of the system. Now, in doing so, I had to do work. Now, you're going, well, how did I increase entropy? Well, if you look at by me moving around, right, I'm going to walk around, I'm going to shuffle papers, right? Okay, hey, I don't need that anymore. Okay, can make that go away. Don't need those two. Okay, don't need that, right? So I'm going to fold that up, okay? So my body is giving off thermal energy, okay? So I'm warming up the air around me. I'm moving through the nitrogen and oxygen molecules that make up the room. So when I move, I disturb them. So I come over here, right? Okay, hey, don't need that. All right, there's a good start. Okay, hey, I threw away the first thing, right?
Good job, Bird.
I know, it's a start, right? Baby steps, baby steps. I can see a little bit more of my tabletop.
You're gonna need something that was in there.
You're just gonna need, he's literally something from physics that he needs.
That I'm gonna need later.
And he's gonna be pissed.
I'm gonna go like,
and
damn it, this is why I don't clean.
You're
Okay.
gonna be pissed and go through the whole recycling.
Yes,
and
and it's like, God, where did that go?
create even more entropy in the room.
Yeah, then I have to disorganize it or increase the entropy. Okay, So here's the thing. The tabletop of your room, whatever it is not going to organize itself. So when you decrease the entropy of your room, okay, call that the system, you increase this energy or the entropy of the surroundings. Because you're going to be moving through there. Your body is going to be giving off energy, okay? You're going to be giving off heat. You're going to be disturbing the air in the room. So while you can decrease the entropy, overall, you're increasing the entropy of the surroundings, okay? So if mom and dad come in and say, hey, you need to clean your room, it's like, I'm just going to increase the entropy of the, of the surroundings. They said, we don't care. Because your mom and dad focus on the system, which is your room, okay? They're just focusing on the system. They can care less about the surroundings. So that's a null and void argument. I'm telling you, you're not going to win. All right. So let's say that we're going to look at making a nail rust, okay? So here's the basic shortcut version of a nail rusting. So we're going to go from a solid iron, and that iron is going to react with oxygen in the air, and we're going to form Fe2O3. Now, what happened to the entropy since we went from a solid and 3 moles of gas down to no moles of gas? So what happened to the entropy?
It decreased.
Overall, the system decreased, right? So in this situation, and this is just one example, we're going to look at a lot more. But you can just look at what happens in terms of the reaction and say, wow, is this going to increase the entropy of the system or decrease the entropy of the system? And a short version of this is just look at what happens with the moles of gas. Hydrogen and oxygen combine to produce water. Oh, I end up with fewer moles of gas. Now, look at any explosion, okay, that happens. Guess what? That works by greatly increasing the number of moles of gas, because that's what creates that overburden of that pressure, because that's going to release that energy and you're going to produce more moles of gas. All right. So, if delta S is negative, delta S with the surroundings is positive, so delta S in the universe is positive and the reaction is spontaneous. So this is what I'm talking about here, is that for the system, I'm going to have a negative delta S. But we know this reaction is spontaneous, okay? Because if you've ever let a nail sit outside, you know that it rusts. So even though I'm decreasing the entropy of the system, I'm increasing the entropy of the surroundings, and that's a positive value that has to be bigger than that negative value. I get a positive delta S for the universe. The reaction is spontaneous. Okay, so on Monday, we will start off here. So let's call it a day.
So how does rust, get off?
Because you're forming bonds, and when you form those bonds,
When you form bonds, you release the energy.
yeah, because you're forming all of these bonds
Yeah.
here, and that's what's releasing that energy. Yeah, you're not going to like, ooh, I'm cold. Let's let nails rust, okay?
I'm cold. Well, you might.
Well, you might.